Hello. In this video, we begin the study of normed vector spaces. We are interested here in the study of norms. For this, we will discuss 2 points. First, a point concerning the definition of a norm. Then we will tackle an exercise on norms. In the first exercise, we consider a function n from a real vector space E to R, which satisfies the 3 properties that which are commonly known, typically in the definition of a norm. Here, we do not specify that n maps to R+, and we demonstrate that with these 3 points, separation, homogeneity, and the triangle inequality show that n is positive. In the second exercise, we consider a function from R2 to R, defined by a sub. Quant varied in R, and we are asked to show that n is a norm and to define the closed unit ball for this norm, or for the distance associated with this norm. Let's start with the first point. We have that satisfies n of x not equals 0 implies x equals 0. We also have n of lambda x equals the absolute value of lambda times in the form of x. And we have the inequality, so n of x plus y less than or equal to n of x plus n of y. This for any x, for any y, for any lambda. Here are the 3 points at our disposal. With these 3 points, we need to prove that n is positive. So, what happens first for x equals 0? What is n of 0? Then, according to homogeneity, we can write it as equal to n of real times 0 of e. It is the absolute value of 0 times NHC of 0 of e, which equals 0. So we have already in 0e equals 0. Starting from this relation, n of 0 is also m of x minus x, x being any element of E which is bounded by n of x plus n of minus x, and thus we obtain that 0 is bounded by n of x plus the absolute value of minus 1 times n of x. In other words, 0 is less than or equal to 2n of x. So we will note here that positivity is a consequence of the 3 properties we give for a norm. It is therefore not necessary to specify that n maps to R+. We now look at the exercise. We have n defined by n of xy equals the SUP over R of, when t varies in R, of the absolute value of x plus y sh of t over ch2 of t. First question, show that n is a norm on R2. Secondly, if d denotes the distance associated with n, determine and plot the closed unit ball associated. So determine b. Now, first question, we will show that n is a norm. So in this type of question, when n is defined by a SUP, we must first prove its existence In other words, we need to prove that the set of real numbers of the form absolute value of x plus y esh of t over ch squared of t when t describes are for given x, y admits a supremum. For this, it is enough to verify that it is bounded above. We will therefore try to bound it by a quantity that does not depend on t. We can already write that the absolute value of x plus y sh of t over ch squared of t is bounded above by the absolute value of x plus the absolute value of y times the absolute value of sh of t over ch squared of t. So, if we want to bound it by an expression that does not contain t, note that if the absolute value of sh of t is less than or equal to 1, we can already bound it. Absolute value of x plus absolute value of y times the absolute value of sh of t by the absolute value of x plus the absolute value of y. And thus, the ratio is also bounded above by the absolute value of x plus the absolute value of y, since the denominator ch2 is greater than or equal to 1. Second case, if the absolute value of sh of t is greater than or equal to 1. In this case, we will note that the absolute value of sh of t is less than or equal to the absolute value of sh2 of t or sh2 of t, since it is greater than a positive. So we can therefore bound the absolute value of x plus the absolute value of y, the absolute value of sh of t, by the absolute value of x plus the absolute value of y. ash2 of t, or the absolute value of sh2 of t, over ch2, that is to say 1, plus sh2. Here we notice that the coefficient of the absolute value of x is 1. The coefficient of the absolute value of y is sh2. If we bound both coefficients by 1 plus sh2 and simplify, we find that it is bounded by the absolute value of x plus the absolute value of y. I repeat, we bound 1 by 1 plus sh2, so the absolute value of x times 1 plus sh2 plus the absolute value of y times that 1 plus sh2, and we simplify by 1 plus sh2, and we find exactly this bound independent done of t. This bound is therefore valid both when the absolute value of sh of t is less than or equal to a, and when the absolute value of sh of t is greater than or equal to a. The set in question is therefore bounded. Consequently, it admits a supremum which confirms the existence or the fact that n is well defined. It remains to verify the three properties we mentioned at the beginning. First property, separation property. If n of xy is 0, that means the sup is 0. The terms that are there are all positive or 0, so this is equivalent to saying that for any t, x plus y sh of t is 0, which immediately gives x equals y equals 0. It suffices to give a t or value for t. For t equals 0, we have x equals 0. For t different from 0, we have y equals 0. Secondly, for homogeneity, it's simple. It suffices to note that n of lambda times xy is the sup of the absolute value of lambda x plus lambda y sh of t over kh squared of t. When t decreases, in this absolute value we can factor out the absolute value of lambda. We can therefore take this constant out of the sup, and we indeed obtain the absolute value of lambda n of xy. The triangular inequality remains. We want to arrive at n of xy plus xy being less than or equal to n of xy plus n of xy. For this, first note that the absolute value of x plus y hash of t on CH2 of t is bounded by the absolute value of x plus y hash of t. The prime names first on CH2 plus the absolute value of the rest, x prime plus y prime sh of t on CH2. Thus, the sup of the first member, when t ranges over R, is bounded by the sup of this sum when t ranges over R. But the sup of the sum is bounded by the sum of the sups, which gives exactly the triangular inequality. Second question. We aim to determine here the unit ball for the distance d associated with n. We have the distance from 0.0 to xy, which is exactly the norm of xy. Thus, a point xy belongs to B if and only if the sup is bounded by 1. The terms that are there, therefore, are all bounded by 1. So this is equivalent to, for any t belonging to R, the absolute value of x plus y sin shish t over ch squared t is bounded by 1. If we want to remove the absolute value, it gives two expressions. This is equivalent to, for any t belonging to R, x plus y sh of t is less than ch squared of t. And minus x minus y sh of t is less than galaxy h squared of t. So, a more point. So, x, y, and b, it's only if for any t belonging to R, we have these two inequalities. X plus y sin of t is less than or equal to cosh 2, that is to say 1 plus h2, and x minus y sin of t is less than or equal to 1 plus sin 2. So let's start with the first inequality. For any t belonging to R, x plus y sin of t is less than or equal to 1 plus sin 2. Note that we can replace sin of t with capital X. This is equivalent to saying for any capital X belonging to R, x plus y capital X is less than or equal to 1 plus x squared. This is due to the fact that the function that associates t with capital X is equal to sinh t, which is a bijection from som R to R, and thus saying that t describes R is equivalent to saying that capital X describes R. And if we look at the obtained relation, it becomes for any x belonging to R, x2 minus y capital X minus small x plus 1 is greater than or equal to 0 by moving these two terms to this side. Here we obtain, if we look at this as a function of capital X, a quadratic trinomial that is always positive or 0 of the sign of its highest degree term. So this is equivalent to saying that its discriminant is negative or 0, which gives us this first relation y2 plus 4x minus 4 is less than or equal to 0. If we look at the second relation, if in this second relation we also replace h of t by capital X, there is equivalence. We obtain the trinomial x2 plus y capital X plus small x plus 1 greater than or equal to 0 for any x in R. This is equivalent to saying that its discriminant is negative or 0. So x2 minus 4 times x plus 1, negative or 0, which gives us the second relation, namely x2 minus 4x. So here it is, as you can see. Of course, y2 for x1, so it's y2 for x4, less than or equal to 0 then. In the first, in the other, yes, we found y2 for x4, and so we find here a second relation, and for a point xy to belong to B, it must satisfy both. In this particular case, specifically in this context, it is important to note that, therefore, consequently, moreover, additionally, furthermore, in conclusion, ultimately, as a result, in summary, to clarify, to elaborate, to illustrate, to emphasize, to highlight, to point out. Note that if we take the equalities, these two relations will define two parabolas that we express in the form of x as a function of y. The first gives x equals minus 1 because y squared plus a, and the second gives x equals 12e to 1. And therefore b, this is the set. The inequalities will now be translated in the form. This is the set of xy such that x greater than equal to 12y2 or 1, since this is less than 0. That means if we pass x here, that means x is greater than equal to 12y2 or 1 enter the set of xy such that x is less than or equal to 12y2 or 1. If we plot this on a graph, we obtain there we have the parabola x equal to 12y2 or 1, and there we have x equal to 12y2 or 1. For this one we are on the left side, and for that one we are on the right side, and therefore b is represented by this part of the plane which is assured. Here is the unit ball for the distance d associated with the norm n. This is a mathematical concept where the unit ball is defined in the context of a specific distance metric d that is closely, thank you,